this session today we will talk about Fourier transforms, the conditions under which Fourier transform exists and what are the different properties of Fourier transforms. So, let us start this. Okay, let us look at the introduction first. Non-periodic signals can be represented with the help of Fourier transforms. Earlier, if you remember, we have seen that generally Fourier series is applied for only periodic signals. But when you find a non-periodic signal that is coming into picture, then we use a Fourier transform for that. Second is, the Fourier transform provides effective reversible link between frequency domain and time domain representation of signals. That means, let us see, okay, let us see I have a wave. Okay, you have a certain signal here. Let us say this is x of t. This is a time domain representation. Now, I want to convert this into a domain which is nothing but f here. That is, this is frequency domain. Okay, and then let us say this is x of f. So, when I want to translate a signal from time domain into frequency domain, we use what is called as a Fourier transform. Okay, this is the Fourier transform. So, whenever time domain has to be converted into frequency domain, we use Fourier series. Now, let us say that I have a frequency domain. I want this frequency domain to be mapped into time domain. Then we call this as, of course, it is called as a inverse Fourier transform. Okay. So, we see here there is a signal here, this is in time domain, there is a signal which has to be represented in frequency domain. So, given a time signal, we use Fourier transforms to convert this into a frequency domain. And let us say you have a signal which is in frequency domain, I want this to be converted into time domain, then apply inverse Fourier transform, I will get a frequency, I will get a time domain representation. When I have a frequency signal or I have a signal in the frequency domain, when I want to get a time domain signal, I use inverse Fourier transforms to get the time signal representation. Okay. Now, we will see that a non-periodic signals, T naught tends to infinity. So, when the time is extended to infinity, what is the frequency? The frequency is becoming 0. Okay. Therefore, the spacing between the spectral components becomes infinitesimal and hence the spectrum appears to be continuous. So, as T increases in the resulting spectrum, the spectral lines become closer and closer. Therefore, a non-periodic signal will be having a continuous spectrum. So, let us understand this a little bit on the board. Now, for a non-periodic signals, T0 is tending towards infinity. When T is tending towards infinity, what is happening to your frequency? The frequency is becoming 0. That means, for example, let us say I have a spectrum like this. This is a frequency spectrum. Now, as the frequency is becoming less and less, small and small, what happens? They tend to move nearer to each other. That means, now this particular one will move here, this will move here and this will move here, this will move here. So, what is happening here? These spectral components are coming closer to each other. So, now the spectrum appears to be continuous. That means, we have started with a signal which is aperiodic, that is which is not periodic, whose period is tending towards infinity, the frequency is becoming 0. So, when I translate this into a frequency domain, the spectral components come nearer to each other. That means, now the signal is becoming periodic. So, when I apply a Fourier series, the signal becomes periodic here. In other words, we can say that a periodic signal, when it have a frequency spectrum, when I draw its spectrum, the spectrum appears to be continuous. Okay, let us go to the next slide. Now, Fourier transform applies for both periodic as well as aperiodic signals. That means, I can apply for a periodic signal, also I can apply for a signal which is not periodic. Now, there are three types of Fourier transforms. The first one is called as a continuous time Fourier transform, which is our topic for this complete session, for this session. Then we have a discrete time Fourier series, then we have what is called as a discrete Fourier transform. These are the different types. So, our concentration for some more sessions of this session will be on continuous time Fourier series, Fourier transforms. It will be on continuous time Fourier transforms. So, let us start with the continuous time Fourier transform. Let us first discuss what is called as a Fourier transform pair. Okay. There are two types here. One is called as a synthesis and the second one is called as analysis. So, what is synthesis here? Synthesis means given a component or a signal in frequency domain, how I get the time domain representation. This is called as synthesis. The reverse of it, that is when a signal is in time domain, how do I get a frequency domain? That is called as analysis. So, as you see here, given f of j omega, we will get f of t by this formula, that is f of t is equal to 1 by 2 pi integration minus into plus infinity f of j omega e to the power of j omega d omega, that is synthesis. Then if I want to know what is f of j omega, then that will be equal to, given f of t, that will be equal to integration from minus into plus infinity f of t e to the power of minus j omega t dt. These are the two formulas. It is called as the Fourier transform pair. Why it is called transform pair? Because given a frequency domain representation, I am able to get a time domain representation, that is called a synthesis. Given a time domain representation, I am able to get a frequency domain representation, that is called as analysis. So, these two form the what is called as a Fourier transform pair. So, if a time domain signal is given and if I calculate the frequency domain, it is called as a Fourier transform. And when a frequency domain signal is given and when I calculate the time domain signal from the given frequency domain signal, it is called as a inverse Fourier transform. So, these two are what we have seen earlier also. So, we have a Fourier transform, then we have a inverse Fourier transform. So, these two form a pair. So, another representation we have given here, x of omega, we can say it as equal to minus and plus infinity x of e to the power of minus j omega t dt, or I can represent in terms of f also. So, it will be x of f, also we can write it as minus into plus infinity x of t e to the power of minus j omega t, j omega we replace it by 2 pi. So, it will be 2 pi f t df. So, that will give you the Fourier transform pair. These are the formula which you should remember. Then the inverse Fourier transform we have given here, that is the representation of inverse Fourier transform as we have already studied, seen in the earlier slide. Is just we are trying to put it again. So, time domain, if I convert into frequency domain, it will becomes a Fourier transform, and given a frequency domain, if I convert back into time domain, it becomes the inverse Fourier transform. That is what we have seen here. So, the double headed arrow indicates that there is for every Fourier transform there exists a inverse Fourier transform. That means, if t is known, I can calculate f, and if f is known, I can calculate t in terms of signals. We have seen earlier what are the conditions under which a Fourier series exists. These conditions are all called as Dirichlet conditions. The same conditions are applicable even for a Fourier transform. Let us see them here. Okay. We have already seen earlier also, we said that Dirichlet conditions are sufficient conditions. So, what is sufficient condition here? We want the signal f of t to be absolutely integrable. That is, if I integrate this given signal f of t, mod of f of t, and from minus infinity to plus infinity, the value which I get must be less than infinity. So, this is called as a absolute integral. This is the one condition which we all have to see, and this is sufficient condition. Once this condition is satisfied, the Fourier transform does exist for the given signal f of t. Then let us see the continuous spectra for this. Given f of j omega is equal to minus infinity to plus infinity f of t e to the power of minus j omega t dt. That means, if a frequency, we are calculating the frequency domains equivalent of the signal whose time signal is given, that is f of t is given. So, if you see here, the frequency signal f of j omega can be broken into two parts. One is a real part and the other one is an imaginary part. So, real part we are indicating by the letter, capital letter Fr, and the imaginary part we are indicating by Fi. So, j is an indication which is the complex component. So, we have a real component and a complex component. So, here if you draw this, I will have the amplitude of the spectrum, we are indicating it by mod of f of j omega, and there is a phase angle associated with it, that is e to the power of j phi of omega. So, if you see here, the figure shows the mapping between the real component and the imaginary component of f. We see here, we are showing this f of j omega, the amplitude of it, and also we are showing you the what is the phase angle that we are indicating by phi of omega. So, this is the magnitude, f of j omega gives you the magnitude, and this gives you the phase of the spectrum. So, any frequency domain spectrum can be represented in terms of its magnitude and also in terms of its phase angle. So, what is the magnitude? The magnitude is given by square root of xr omega square plus xi omega square. The phase x of omega is given by tan inverse xi of omega divided by xr of omega. So, this is we are trying to show you in two different notations, either I can use f or either I can use x also. Invariably both are actually same, they can be used in either ways. So, this is the phase angle. Now, if I plot the graph of the mod of x omega versus omega, it is called as the amplitude spectrum. That means, I will take omega versus the amplitude of it. How we have calculated? It is calculated as the square root of the real part plus the imaginary part. So, if these two are plotted together, it is called as the amplitude spectrum. And if I plot the phase angle of the given signal versus the frequency, it is called as the phase spectrum. So, these two plots together are called as frequency spectrum. So, a frequency spectrum I can draw in two ways. I will have an amplitude spectrum plus I will have a phase spectrum. Okay, we can just see an example here. Let us see an example here, a small example. Or let us take a signal. Let us say I have a signal like this. Okay, this is x of omega versus omega. Okay, so this is, what is this called? This is called as the amplitude spectrum. Let us say there is a phase angle here. Now, let us plot this with respect to the phase, okay, and this is omega again. Let us say I have something like this. Now, this is called as the phase spectrum, and amplitude spectrum plus phase spectrum is called as the frequency spectrum. Okay. So, this is the what we have studied. So, we have plotted the amplitude of a given signal and also we have plotted the phase versus omega. So, this is called as amplitude spectrum, this is called as a phase spectrum, and both of them together is called as a frequency spectrum. The example here is, we find a signal which is existing only between -1 to +1. Okay. In all other places it is 0. That means, the integration of f of t that is done from -∞ to +∞ now will be replaced to -1 to +1. Okay. So, what is f of t here? What is the value of f of t? F of t is 1, that is having an amplitude 1 from -1 to +1. Let us see how I can get a frequency component from this. So, we all know the formula. The formula is f of j omega is equal to integral -∞ to +∞ f of t e to the power of -j omega t dt. So, for us now, what is the answer? Now, next step will be, for us what is the next step? The next step is that we have to change the integration limits. The signal is existing only between -1 to +1. So, change the integrals to -1 to +1, then it will be e to the power of -j omega t dt. Once this is done, if I integrate this, I will get this equal to 1 by -j omega e to the power of -j omega t, and the values for -1 to +1. So, when I do all this, I will get this is equal to this, and convert this into a sine form, it will be 2 sin omega by omega. That means, a given signal which is 1 in time domain and existing between -1 and +1, its frequency domain representation will be equal to 2 sin omega by omega. So, let us see, this is the plot. So, the first one shows a frequency spectrum, that is, it is having both the phase angle and the amplitude. Okay. Then the second shows just the amplitude of a signal, and the third figure shows the phase angle of this. So, this is how we represent a frequency domain signal. So, what we have done, we started with a time domain representation, converted it using the formula which we know, that is f of omega or j omega is equal to -∞ to +∞, f of t e to the power of -j omega t dt. F of j omega is equal to -∞ to +∞, f of t e to the power of -j omega t dt, that formula we have used. Then the limits -∞ to +∞ are replaced by the actual limits of the given signal. So, in our case it is -1 to +1. So, it will be minus integral -1 to +1, and then what is the value of f of t here? F of t for us is 1 here. So, 1 into e to the power of -j omega t dt. and after that we have calculated the integral of it, then we got the answer, final answer, which is equal to 2 sin omega by omega. So we have plotted the frequency spectrum, the first figure, then we have plotted the amplitude spectrum, then we have plotted the phase angle. So all these three are plotted together. So these three will indicate how a signal which is represented in time can be represented in frequency domain. Okay, let us see another example. If you look at this example, this is an exponentially decaying function, e to the power of minus alpha t. So now we have to calculate, this is in time domain, so we have to calculate what is its frequency domain representation. See here, again we have applied the same formula. The formula is f of j omega is equal to minus into plus infinity f of t e to the power of minus j omega t dt. Okay, let us again replace the limits. Now what are the limits now? The limits will be from 0, isn't it? So it will be 0 to infinity e to the power of minus alpha t into e to the power of minus j omega t dt. So when I integrate this, the next step will be 0 to infinity integral e to the power of minus of alpha plus j omega t dt. So that will be equal to 1 by alpha plus j omega. So this will be the frequency domain representation of an exponential signal which is existing from 0 to infinity, that is e to the power of minus alpha t u of t. Okay. So this is your answer, that answer is equal to 1 by alpha plus j omega. Now this is the amplitude spectrum plot and the phase plot. See the amplitude and then see the phase angle. So this is how it exists. The amplitude spectrum and frequency spectrum are plotted for this. Now we have some very important notes here. There are 3 points which we have to discuss here. One is the power signals generally are periodic signals. So we apply Fourier series to them. In fact, we calculate the Fourier series of a given power signal. But when I talk about the second point generally the energy signals are non-periodic. So the Fourier transform is calculated for them. Okay, if you remember the formula for earlier P, the integration of P was done for a certain period, minus T by 2 to plus T by 2L. Okay, P is generally, that's why it is called as a periodic signal. Whereas when I talk about energy signal, it is a summation of series of signals from minus infinity to plus infinity. So energy signal generally is aperiodic. So we calculate a Fourier transform for energy signal, and for a periodic signal like a power signal, we calculate the Fourier series for it. Okay, and as we already mentioned, the Fourier transform can be applied for both a periodic signal and a non-periodic signal. Let us see what are the merits of using Fourier transform. The first merit is the original time function can be uniquely recovered from it. The second point is it has property analogous to a common logarithm that helps in evaluating convolution integrals. And the Laplace transforms used to solve transient problems, whereas Fourier transforms are very useful in communication systems. So whenever there is a transient involved, we always go for a Laplace transform, and whenever we talk about a communication system, we always use a Fourier transform for this. Then what are the limitations? If we talk about the limitations of Fourier transforms, the first limitation is the Fourier transform is very closely related to Laplace transform. If we call this as a limitation, they are almost same. The only difference is their S is there, which is replaced by j omega here. So that's the only difference. S has been replaced by j omega. That is, S is equal to sigma plus j omega, that is omega, sigma is missing. Sigma is nothing but a damping factor that is not existing. So, there is a second limitation. Okay, in a Fourier transform, the damping factor is 0. So, the Fourier transform may not converge for many functions. So, most of the Laplace transforms, in fact, they converge because the sigma plus j omega, sigma is a damping factor. So, the damping factor dampens out. So, there is a convergence that always happens for Laplace transforms. Because this damping factor is 0, in the case of a Fourier transform, the convergence problems arise in Fourier transforms. That is one of the major limitations of Fourier transforms. Now, let us look at different properties of Fourier transform. Let us look at continuous time Fourier transform properties. These properties are very important. Okay? Before actually we go into the Fourier transform properties, let us see what are the notations which we are using during the whole class. So, this is the notation. So, we are using f to indicate Fourier transform. So, f of t is equal to f of j omega. That is Fourier transform. F inverse of f of omega is f of t, that is inverse Fourier transform. So, f we are using for Fourier transform, f inverse we are using for inverse Fourier transform. So, we again use a double headed arrow here, f of t, if I get f of j omega, it is called as a Fourier transform. Okay? And when I reverse it back, I will get f of t, the double head arrow, it flows in this direction, then that becomes inverse Fourier transform. We use the letter F to indicate the Fourier transform, F minus to indicate the inverse Fourier transform. So, this is the notation which we are going to use throughout our discussion about the Fourier transform properties. The first property is called as linearity. This is also called as a superposition property. So, what does it say? It says I have two functions f1 of t and f2 of t. Both of them have a Fourier transform. That is, you have f1 of j omega, capital F1 of j omega and capital F2 of j omega. So, these are the Fourier transforms that are existing for the given functions. So, the first function f1 of t is multiplied by a certain scaling factor a, and the second function f2 of t is multiplied by a certain scaling factor b, and both of them are added. Okay, this is also called superposition. So, both of them are superimposed on each other, that is, they are added. The resulting Fourier transform also will be an addition of the Fourier transform of f1 of t, Fourier transform f2 of t, and which are equally multiplied by a for the Fourier transform of f1 of j omega and multiplied by b for the Fourier transform f2 of j omega. So, that is what we see here. So, what does it say? It says a1 f1 of t plus a2 f2 of t will, if I calculate the Fourier transform of these, I will get a1 f1 of j omega plus a2 f2 of j omega. As I have told you, f1 of t is having a Fourier transform f1 of j omega and f2 of t is having a Fourier transform of f2 of j omega. And again the multiplication factor a, b or a1, a2, whatever it is here. Here we are using a1 and a2. We look at what is called as a time scaling property. So, now here the time signal is scaled by a factor a. Let us say the signal is f of t, now it is scaled by a factor of a. So, what will be its corresponding Fourier transform? As you see here in the PPT, as you see here in the slide here, f of at is having a Fourier transform which is f of j omega by a, and this is scaled down, that is 1 by mod a f of j omega by a. This is the time scaling property. Okay. So, this is time scaling property, a little bit of this more later. Then we look at what is called as a time reversal property. So far we have seen that f of t is having a Fourier transform f of j omega. So, what will be the Fourier transform of a signal which is reversed in time? That is f of minus t. As you see here, f of minus t is having a Fourier transform f of minus j omega. Let us see the proof for this. Here f of minus t. So, what we have done is integration of minus into plus infinity. F of t we are replacing it with minus t. So, f of minus t e to the power of minus j omega t dt. Okay. Next, here if I look at this, f of minus t e to the power of minus j omega t, we have done it here. D has to be replaced by minus t as what we have done here, and minus j omega t has become plus j omega t. So, the next step is this. So, finally, we have seen that this is nothing but. So, what is the process what we have applied here? We have seen that f of plus t, we have introduced minus t here, and e to the power of minus j omega t will become e to the power of plus j omega t, d of t will become minus d of minus t. So, ultimately we got a formula which is equal to minus into plus infinity f of t e to the power of plus j omega t dt. So, f of t, f of omega, if f of t is given, it is f of omega. If f of minus t is given, you see there is a change in the signal, in the sign. There is a change in the sign. Earlier it was e to the power of minus j omega t, now it has become e to the power of plus j omega t. So, this is nothing but f of minus j omega. Okay. So, this is the proof for a time reversal property. So, whenever a signal in time domain is reversed in time, that will be equivalently reversed in frequency domain also. Now, let us look at the next property called as the frequency shifting property. It is also famously known as modulation property. So, what does it say? When a time domain function is multiplied by a factor e to the power of j omega naught t, it will be a shift in frequency in the frequency domain representation, that is f of t into e to the power of j omega naught will have a Fourier transform which is f of j of omega minus omega naught. That is, there is a translation. The frequency signal which is existing at f of omega is equal to 0 now exists at omega is equal to omega naught. So, there is a shift from 0 to another frequency, that is, it is getting translated from 0 frequency to omega naught frequency. This is called as frequency shifting. It is also called as a modulation property. So, I repeat, f of t e to the power of j omega naught will have a frequency domain which is equal to f of j of omega minus omega naught. This is the frequency shifting property. Let us look at the next property called a symmetry property. That means the Fourier transform of f of jt is equal to 2 pi f of minus omega. This is called as the symmetry property. Let us look at the Fourier transform for real functions. That means if f of t is real function and f of j omega is fr of j omega plus j of fi j omega, then f of minus j omega will be equal to f star of j omega, okay, because f of t is a real function and f of j omega is equal to, we all know, minus into plus infinity f of t to the power of minus j omega t dt, and f star of j omega will be equal to minus into plus infinity f of t e to the power of j omega t dt instead of minus j omega t. F star of j omega will have minus into plus infinity f of t e to the power of plus j omega t dt. This is nothing but f of minus j omega. Okay. So, this is for a f of t which is a real function. Now, f r of j omega is even function and f of I of j omega is a odd function. That means, f r of minus j omega will be equal to f r of j omega, because this is an even function. F I of minus j omega will be equal to minus f I of j omega for a odd function. So, there is a very important point which we are making in this slide, that is, the magnitude spectrum of a real function f of t in its frequency domain, that is f of j omega, is even, whereas the phase spectrum phi of omega is odd function. So, we have to remember this. This is a very important point which has to be remembered. So, I repeat this: magnitude spectrum f of j omega is even and the phase spectrum phi of omega is odd. Okay. Fourier transform for real functions. If f of t is real and even, f of j omega is real. If f of t is real and odd, then f of j omega is purely imaginary. Okay. We do not need the proof here. Now, let us see the next property of Fourier transform. What is the Fourier transform of a derivative of f of t? It is called as f dash of t. So, if f of t is having a Fourier transform f of j omega and the limit t tends to plus or minus infinity f of t is 0, then f dash of t will have a Fourier transform which is j omega f of j omega. That is, when I take the derivative of a time domain function, its frequency domain function will be multiplication by a factor j omega multiplied by its Fourier transform, that is f of j omega. Similarly, I can extend to the nth derivative. So, the same conditions exist here. So, what will be the nth derivative? So, that will be equal to j omega to the power of n f of j omega. So, n can be 2, n can be 3, n can be 4, n can be any number. So, whenever I have nth derivative, then the formula is j omega n f of j omega. Fourier transform of an integral function. So, earlier we have seen derivation, now we have to see integral of it. So, again the condition is f of t has a Fourier transform which is f of j omega and the limit minus into plus infinity f of t dt is equal to f of 0 is equal to 0. These are the conditions which exist. Then when I take the Fourier transform, the integral of f of x dx, that is from minus into plus t, then the Fourier transform will be equal to 1 by j omega f of j omega. Okay, this is the Fourier transform of integral. Integrate in the time domain, that is f of integral minus into plus t f of t dt will have a Fourier transform which is equal to 1 by j omega f of j omega. So, this is the Fourier transform property for integrals. So, the next property is when I take the Fourier transform of the derivative of the Fourier transform. When I take the derivative of the Fourier transform, what will be the equation? So, Fourier transform of minus jt f of t will have a Fourier transform d of f of j omega by d omega. That means, when I take d by d omega of f of omega, it will have an inverse Fourier transform where the time domain function is multiplied by a factor that is equal to minus jt. Okay, that is what we get here. That is the transform property.